So why am I posting this video? Recently I designed a CPU system based on the 8088 and with IBM PC compatibility. It's the third CPU card which I've made for my simple backplane system. I needed to learn more about the hardware of the 8088 CPU, which I will discuss in this video, as well as further knowledge of the CPU instruction set, which I won't discuss in this video. The 8088 CPU card will be covered in a future video with a full description of the design for those that are interested. So the 8088 is one of a pair of CPUs which includes the 8086, which was designed and manufactured by Intel, and of course due to historical reasons the instruction set of the 8088 still is there in modern day PCs. As is common for the time, the 70s and 80s, microprocessors and microcontrollers would normally be packaged in a 40-pin dual inline package. It has a 5-volt power supply, it's got about 30,000 transistors, and the process is 3.2 micron. Just for comparison, nowadays the process node is down to about 14 nanometer, even 10 nanometer cutting edge processes. So it's quite a long time ago. And InMOS call this HMOS. HMOS is a variation of NMOS. In NMOS the design is based on N-channel MOSFETs, compared to CMOS, in which the design is based on both N and P channel MOSFETs. It's a 16-bit CPU architecture. It's got a 20-bit address which gives it 1 megabyte of memory address range, and a feature known as segmentation is used to use two 16-bit registers, essentially a base and an offset, to construct a 20-bit address. The 8088 is a version which has an 8-bit external databus, and this was one chosen for the IBM PC. The 8086 has a 16-bit external databus, and as a consequence the 8086 is slightly faster than the 8088 because it can fetch 16 bits at a time rather than just 8. Both CPUs have small instruction queues, and the one on the 8086 is a little larger. Both of them interface to the 8087 Maths coprocessor. An interesting feature is you have to choose the mode that the CPU is configured in. That's pretty unique to this processor, and there's something known as minimum and maximum mode, which I'll cover later on in the presentation. Also, common to processors such as the Intel 8080, which was inherited by the Zilog Z80, is the idea of having not only memory address space but having I/O address space and I/O instructions. Although the 8088 has a 20-bit address, only 64K can be addressed as I/O locations. This is the 8088 CPU configured for minimum mode. Intel have slightly different names depending whether you're on minimum mode or maximum mode, and this is the 8086 in minimum mode, and I'll explain very shortly the differences between the two. So in the following slides the pinout differences between the 8086 and 8088 in minimum mode are highlighted in red. All read and writes use AD7 to AD0 on the 8-bit databus 8088. And on the 8086 we have 8 additional AD pins, giving us AD0 to AD15. If we compare the 8088 in minimum mode to the 8086, and I'll do that by page swapping, the pins in red are the ones that have slightly different names or functions. For the 8088, the bottom 8 pins of the address bus are shared with the data bus and are known as AD pins, but the upper 8 bits of the address bus have dedicated pins. If we look at the 8086, the AD bus is now 16 pins because the data bus is the low 8 bits and the high 8 bits. Pin 34, bus high enable, is used to indicate whether a read or write is taking place on the lower or upper data bytes. Pin 28 is a pin that says whether we're doing a memory access or an I/O access, and again the polarity for some reason has changed between the 8088 and the 8086. That's just something to be aware of. Now, when we come to using the 8088 or the 8086, there's the special significance of the AD pins. AD pins have been common on a number of Intel processors and others as well, and the idea is that the AD pins are able to be dual purpose. They can carry the address and they can also be used for data read and write. The address is needed at the start of a memory access, and so the idea is it gets latched, and that's where we have this special signal called ALE, or address latch enable, and on the falling edge of ALE the address is latched from the AD pins into some external circuitry. The recommended chip to use is an 8-bit latch. There are a number of different ones to choose. The one I've shown here is the 74LS573. That particular latch has a nice feature that the data pins are on one side and the Q outputs are on the opposite side. There's a more common chip, which is the 74LS373, where the pin out is not quite as convenient. So I would always recommend using the 74LS573. Also, you will notice that on the 8088 we have to for sure latch the address of AD0 to AD7. A8 to A14 and A15 do not need to be latched. They hold the address and are not dual purpose pins. However, the upper 4 address pins, A16 to A19, are dual purpose, but they don't carry data information, they carry status information, so they also need to be latched as well. Now, the one pin that's not yet been discussed is the 74LS573 has an output enable that can be used to tri-state Q0 to Q7, and that's particularly useful if you want to implement some kind of DMA on your 8088 system, as I did on my own CPU board. So minimum mode, the idea is that we don't need much external circuitry to interface the CPU to standard memory chips. We have a not read pin, a not write pin, which are your standard read and write strobes to be connected to memories, RAMs or ROMs, EPROMs. And we've got a couple of pins which can be used to control a tri-state buffer on the data bus. DT/R, data transmit stroke receive, and not DEN, data enable. For a truly minimum system, you probably don't need to use DTR or DEN. However, you will for sure need to use not read and not write. And you can see that pin 33 needs to be held to +5 volts or logic high to select the minimum mode configuration of the CPU. So moving on to some more pins, we have some pins dedicated to interrupts, which is a standard feature of most microprocessors. The NMI is the non-maskable interrupt. It's edge triggered on a low to high transition, However, there is a minimum pulse width, but that's not very difficult to meet. As its name implies, and as is the case with the similar pin on many other processors, this interrupt can't be masked off in any way. So it would be used for the highest priority purposes. On the IBM PC, it's actually used to print a message if there's a parity error on the memory bus. INTR is the interrupt request. This is level sensitive, active high, and internally synchronized, and it can be masked off using the CLI instruction and re-enabled using the STI instruction. It's acknowledged by not INTA. Not INTA is an interesting pin because it can be used with another Intel peripheral, the 8259 PIC or Programmable Interrupt Controller, and when it goes low, that chip supplies an 8-bit vector onto the lower 8 databits and is used to vector the CPU to one of 256 different locations. If we compare it to something like the 6502, it has an IRQ, which is almost identical to INTR, but it's active low. That goes to a fixed location and there's no vector capability. So it was very thoughtful of Intel to design the chip to go along with the 8088 to give us a quite sophisticated interrupt facility where we can have multiple interrupts and going directly to the routine where they're required. On something like a 6502, if IRQ is shared, you've got to do some software polling of the peripherals to find out which peripheral caused the interrupt. So another feature common to almost all CPUs is the ability to tri-state the address and data bus for the purposes of DMA, to let some other peripheral access the bus directly. Now this one is quite interesting because it is different between minimum and maximum mode. So in minimum mode we have two pins, pin 31 and pin 30. Pin 31 is hold, which is the active high bus request, and pin 30 is hold acknowledge, which is taken high at the end of a read or write cycle to tell the peripheral that the bus is now available. If we look at the pins of the CPU, the address pins, the AD pins, not read, not write, memory IO select, DTR, not DEN are the pins which are floated, tri-stated, and on the 8086 the pin not bus high enable is also tri-stated. These pins should then be controlled by whatever peripheral wants to access the memory subsystem, and it has full control to do as many reads and writes as it needs to perform. Now in maximum mode the chip is reconfigured, so we no longer have hold and hold acknowledge. We have a pair of pins, request grant 0 and request grant 1. This allows two DMA masters, and the reason for this is that if you have an 8087, the 8087 needs to use one of these pins. I didn't know a lot about how the 8087 works, a mass coprocessor, but it turns out it needs control of the bus because it needs to do some reads and writes itself. So if you have an 8087 and you only have one way to tri-state the CPU, you have difficulty if you want to use something else to tri-state the CPU. So Intel would appear to have given you two sets of pins, one for use for the 8087 and one to be used by the user. The downside is request grant is an IO pin, and there's a complicated protocol in order to actually put the processor into tri-state and to release it. In maximum mode, the address pins, the AD pins, not read, not lock, the three status pins, not S0, S1 and S2, are all floated, and also not bus high enable is floated on the 8086. So it's interesting to talk about interfacing the 8088 or 8086 with the 8087 maths coprocessor. If you look at the motherboard which I'm currently repairing, you'll see that the sockets of the CPU and the maths coprocessor are next to each other. And if we look at the pinouts of the 8087, we can start to understand why. It's clear that Intel designed the 8087 intimately with the 8088 and 8086 to be compatible in terms of how the bus worked, and also the pins are almost identically placed, which means that PCB layout is greatly simplified. And so you can see the yellow pins where there's a one-to-one mapping, and the red pins are ones where there is a little bit more significance. The pins are still shared. You can see that one of the request grants of the 8088 is used by the 8087, and we can see pin 23 of the 8087 is called busy, and that goes back to the special input called not test on the 8088. Now it's interesting to understand how that works, because if the 8088 executes a floating point instruction, effectively the 8087 takes over and needs control of the bus to fetch the operands, as I understand it. It then crunches the numbers and it raises a busy flag while it's crunching the numbers. When busy goes low, the computation is complete. The test pin is a special pin which is used with the wait instruction, and what happens if the wait instruction is executed and the test pin is high, the CPU just idles and does nothing. So if you look in 8088 code, you will commonly find that immediately following a floating point instruction there is a wait instruction, and so the idea is the 8088 simply waits until the floating point instruction is completed. There's no requirement to do that. You could issue a floating point instruction and then the 8088 can continue to run some other code, but you would have to at some point go and check that the 8087 had finished and actually figure out where the result is. I'll leave it as an exercise to the viewer to read up on the 8087. One thing to note is if you want to use the 8087, the CPU has to be configured in maximum mode. And that was one thing that it took me a while to figure out, is why when the IBM PC was implemented did they choose maximum mode. Arguably maximum mode is a little bit more complicated than minimum mode, although the two modes are subtly similar, and it took me a while to figure out why, but I think that's the reason. Having the option of a maths coprocessor would make sense in a business machine, and so if you're going to implement a system using the 8087, you must put the processor in maximum mode. Min/max needs to be grounded. What is the difference in maximum mode? Well, the most important difference is that a number of pins change their function, and we have a number of status pins now, and they have to be used in conjunction with an external chip, which is the 8288 bus controller. So the 8288 does a number of things. It generates the I/O read strobe, it generates two different timings of I/O write strobes, it generates a memory read strobe, and it generates two different timing of memory write strobes. The strobes MRDC, IORD, AMWC, AIOWC and INT-A are all 2 cycles long. And INT-A is the interrupt acknowledge, which previously came from the CPU in minimum mode. The strobes MWTC and IOWC are only 1 clock cycle long and so are not commonly used. ALE is the equivalent of the same name pin in minimum mode, which was on the CPU. Not DEN and DT/R are the equivalent of the same name pins in minimum mode on the CPU. These are forced inactive when the CEN input of the 8288 is low. Not AEN has to be low for the strobes to be active. When high, it forces the I/O and memory read-write strobes to be inactive. So now I'm going to give some example hardware configurations. If you want to design the 8088 or 8086 into your system, you've got a number of choices to make. The first one is whether you're going to use minimum mode or maximum mode. When I designed my own CPU board, I used minimum mode. The reason was the bus controller is not easy to obtain nowadays, and what's more, it's expensive. So I thought, it's my first time designing an 8088 system, so we'll use minimum mode. I'm not bothered about having an 8087 maths coprocessor. So here is perhaps the most basic architecture of an 8088 CPU board in minimum mode. You must use the 8284 clock controller. The reason is the clock has a strange 2:1 max space ratio, and on the IBM PC the 14.318 MHz clock is divided down to give us a 4.77 MHz clock, and that's a divide by 3. We can see that the min-max pin is held to 5 volts to select minimum mode. We need some kind of strobe decode logic to give us the 4 normal strobes that are useful for interfacing to memory or I/O chips, which is not I/O read, not I/O write, not memory read, and not memory write. And in the simplest case, you can use something like a TTL chip, the 74LS138, or you could use a GAL or other discrete logic. You can see that we need 2 of the latch chips minimum to latch the lower 8 address bits using ALE and the upper 4 address bits A16 to A19, but A15 down to A8 hold their values for the whole bus cycle, so they don't need to be latched, and that will give us the full 20-bit address which can go to our memory subsystem. It's not mandatory to use this, but if we want to, we can buffer the data bus, the AD7, AD0 pins, using a standard tri-state buffer, the 74LS245 or equivalent. And you can see that the 2 pins DT/R and not DEN provided by the CPU go directly to 2 pins on that particular chip, and the timings are such that we're not going to get any contention whatsoever, and then we have a nice buffered address and data bus and the strobes to be used. However, on my own CPU card, I decided I was also going to latch A8 to A15. It's not necessary. What this means is it just gives a symmetry to the system, and now if I want to tri-state the address bus, I only have to worry about the output enable of the 3 74LS573 latches. In my system I was using DMA, and so it made sense to add this extra latch. Otherwise, if you wanted to use DMA, you would need to tri-state the latches but also tri-state A8 to A15. So I think this is actually a nicer solution. So I'm just going to swap backwards and forwards between these 2 implementations just so you can get an idea of the difference. This is a very minimum solution, although you could get rid of the 245, and the only difference here is that we're adding 1 extra latch. No latch, 1 extra latch. Now it's interesting to look at what an 8086 system in minimum mode would look like. And this is what we have here. So now the difference is we still need the latch on the upper 4 address pins, A16 to A19, but now we need 2 8-bit latches because we have 16 AD pins, and so each of the TTL chips latches 8 bits each, the upper 8 address pins and the lower 8 address pins. The data bus is now 16 bits wide, and so we need two 74LS245s if we're going to buffer the data lines. And if I go backwards and forwards between the 8088 and the 8086 in minimum mode, you can get an idea of what the differences are. So now we're moving on to the 8088 in maximum mode, and you can see that we need an additional Intel chip, the 8288, known as a bus controller. We use the same clock controller, the 8284, and you can see that a number of control signals previously coming from the CPU are now coming from the 8288. So the 74LS245, the direction enable, is now controlled from the outputs of the 8288 and not the CPU. Those pins on the CPU now have become used for status output, which goes to the input of the 8288 as shown in the diagram. Address latch enable has become QS0, Q status 0. Q status 0 and Q status 1 are required by the 8087 in order for it to snoop on the data bus to know what is happening with the instruction stream. But in maximum mode, if you're not using the 8087, they're not usually connected anywhere. And again, in this particular example, I've shown that A8 up to A15 are latched, but strictly that's not necessary. So if we start to think about CPU timings, because understanding of CPU timings is important if you're designing a CPU system, we see from the databook that a memory read or a memory write take 4 CPU clock cycles if there are no wait states. And in this diagram here we can see AD7 down to 0, and we can see at the start they carry address data, later they carry data from the memory, then they move back to address data. Now we can label this diagram to get a better idea of what's going on. The 4 cycles needed for either a read or a write are known as T states, as they are on other processors such as a Z80. And we can see that the number of outputs ALE, not read, not write, not DEN, DTR are derived from the input clock. The delays between the clock edge and the edge changing on the strobes is not always clear from the databook, but there's much more information there. That's something I hope to investigate later. Again, this just is to make a clear highlight that the read cycle is 4 T states and the write cycle is 4 T states. The blue line's been added just to illustrate where the address gets latched. So the CPU outputs the address on AD7 to 0, and while ALE is high, the 74LS573 or equivalent is transparent, and whatever on the AD pins passes straight through. But when ALE goes low, the inputs of the latch are latched on the outputs, and so that forms part of the address bus. The AD bus is now free to be used for data transfer purposes, and so we can see in T3 and T4 states we're expecting the data to come back from memory, and the data will be latched by the rising edge of the not read strobe. And if we look at the write, as soon as the address has been latched, the AD lines change to hold the write data, and they're valid for quite a long time. Just giving some further information about the 8088 and 8086 CPUs, there are many second sources, so if you're going to actually look for any on any of the usual websites, don't just limit your search to the Intel parts. There are parts from AMD, Oki, Siemens and the other manufacturers listed there. And in fact, back in the 70s, customers actually wanted chips, particularly CPUs, to be manufactured by a number of companies. They wanted second sources. So in some ways, for the 8088 to be successful, they had to allow AMD to manufacture their equivalent 8088, because they could then go to the market and say the 8088 is not only manufactured by Intel, but it's second sourced by a number of other companies, and it results in competition in the market. Many years later, that competition seems to have waned somewhat, but there was always competition between AMD and Intel. Later, the 8088 and 8086 were available in CMOS, known as the 80C88 and 80C86, and they were made by different companies, including Renesas, Harris and Intersil. So if you're doing searches on websites looking to buy these, they're the companies that you probably find have manufactured the CMOS parts, as well as AMD and Intel. One interesting part that is worthy of mention is the NEC V20. Essentially, it's a pin compatible drop-in replacement from the 8088, but it has some subtle differences. It has some extra instructions which are taken from the 8286. Rather bizarrely, it has an emulation mode where it can emulate the instruction set of the older 8080 8-bit CPU, which was also manufactured by Intel. It's more efficient in its use of clock cycles to complete instructions, which results in the CPU being faster. And one other change, which doesn't impact if you use it as a drop-in replacement, but if you're designing it for a new system, is the strange 2:1 mark space ratio of the clock required by the Intel part has now been relaxed, and you can give it a standard 50-50 mark space ratio clock. I hope you find this information interesting, and I'd encourage any of you out there to go ahead and design your own 8088 or 8088 systems. If you don't want to do that, stay tuned and I'll describe the system that I've designed myself.